We're going to cover VSEPR bond hybridization and molecular shape, polar and nonpolar molecules, along with hybrid orbitals. VSEPR theory is considered to be the overarching theory regarding how electrons are distributed around central atoms. The VSEPR theory stands for valence shell electron pair repulsion theory, which basically states that electron clouds, according to the quantum model of atomic structure, has this force of attraction and repulsion, primarily with the nucleus where there is attraction, and then repulsion among the actual electrons. These are due to Coulombic forces. Coulombic forces are the attraction that you have between two charged particles and allow these atoms or electrons to be able to be attracted to certain areas like the nucleus, and in some cases repelled. When we talk about terminal atoms, we want to talk about electrons want to be as far away from each other as possible. These terminal atoms generally are going to be on the outside, and usually because of this, these electrons and atoms, as they kind of go in, they eventually serve specific geometric shapes. And these shapes are going to be determined by the way these electrons are floating around. So I want you to think of these as these electrons are moving around in these clouds, and as they're moving around, they're going to be bouncing off of each other, creating very, very unique shapes depending on what that looks like. So the first thing for VSEPR is there is an actual process that goes with it. First, you're going to count the number of charged clouds, or what they call bonds, and lone pairs around the central atom. Now, we normally talk about clouds, but when we draw them out, we draw them out as bonds, either with your shared paired electrons or lone pairs if they're considered to be on the outside. There's usually going to be a central atom, and usually what happens is we talk about how they're going to be doing these bonds. So the first thing is, for a single bond, you're going to have 2 electrons. For a double, you're going to have 4. And obviously for a triple, you're going to have 6. A lone pair is going to be 2 electrons, and a single unpaired electron considers to be 1 lone electron, 1 unpaired electron. Part B, we're going to be doing is putting each item is considered to be 1 bond if it's a single, double, or triple, as defined in the previous slide. And then a lone pair is defined as something that only has 2 electrons on the outside, and also an unpaired electron which only has 1. Second thing we're going to do, once we have defined that, we're going to talk about the shape. Now, there are 13 shapes, and you must memorize these by name and by angles. There's no other way around it. My recommendation is get that list and get it going so that you can start memorizing these shapes and these angles. All right, so let's take a look at the first example for carbon dioxide. Carbon dioxide has a charged cloud. There are three elements in here. Well, 2 atoms, and then 3 of them in attachment. It's going to be oxygen, carbon, and oxygen. And in this case, what you're going to have is you're going to have 2 electrons in each of the double bonds. So that's 4, and that's going to be 4. And along here, these 2 lone pairs for oxygen. Now, if you notice carefully, you're going to start seeing that carbon here has to maintain a full octet, meaning that it needs to have 8 electrons to be happy. Oxygen also needs to have 8 electrons to be happy. So what it'll do is it'll put 2, 4, 6, and 8. And so if we take a look at this Lewis dot structure, this satisfies Lewis dot because of the fact that we have the octet and also the fact that we have created these bonds. Now, in VSEPR theory, we're going to talk a little bit about what this shape looks like. So as we take Lewis dot and we take it to the next level, we know that there's 2 charged clouds. And those 2 clouds are going to be obviously the ones attached from the oxygens into the carbon. We know that there's going to be 2 bonds. We know there's going to be no lone pairs because from the central atom. And then we know that it's going to be linear. So we usually define these 3 as areas of the actual structure itself. So the shape that it creates is going to be a linear structure, meaning that it looks like a line. Okay. Now, linear geometry is going to be 180 bond angle. And so if you take a look at the central atom for carbon, there's going to be 2 charged clouds, which are going to be the oxygens here. We're going to go back to the bonds, which are going to be here and here. And obviously, we know that we have no lone pairs on the actual central atom. And so that's why it's a linear shape. So again, memorize bond angles 180 degrees from the bottom and 180 degrees from the top, which gives us the CO2. let's talk about BF3 or boron fluoride. Boron trifluoride is actually going to be another area where we have 3 charge clouds. And again, we're talking about electron clouds, not orbitals in this case. It's because of the fact that these electrons are circulating around the element. Boron's going to be your central one, and then fluorine's going to be here. In this case, fluorine has 2468, and here. But here's something weird. Boron doesn't have a full octet. Boron's one of those exceptions to that rule where it doesn't need to have that full octet. So in this case, we're going to have a charge cloud of 3. We're going to have 3 bonds connected to the boron, no lone pairs, and it's going to be trigonal planar. So trigonal planar is going to be considered to be BF3 because trigonal 3, planar, it's like a regular plane, and then that's going to be the name of it, and you have no lone pairs for that. Trigonal planar is going to have a bond angle of 120 degrees. So if you take the plane and you kind of slice it across between each of the angles right here, you're going to have a 120 degree angle, and that's going to be that 120 that you see. So here we have the F's and here we have the B. Now let's take a look at something where we have a charge on it overall. So this is going to be considered to be NO2, and that's a minus charge. NO2 has an overall charge of a negative, and this is going to be nitrogen, oxygen. And in this case, we're going to see that nitrogen is in the middle because it's the least electronegative than the other two. So oxygen is going to be in this case here. This is also called a polyatomic ion in the sense that we have obviously 2 nonmetals, all nonmetals on top of that, and we have an overall charge of negative. We'll talk about that, where that negative charge comes out later. So in this case, we see that there's a double bond between nitrogen and oxygen because it's 2,4,6,8 and 2,4,6,8, and then nitrogen actually has 5. It comes in with 5. 1, 2, 3, 4, 5, and it makes the octet 2,4,6,8 with an overall charge of negative. So because of that, nitrogen is going to have 3 charge clouds. So we take a look at this example, and you might ask yourself, where is the charge cloud coming from? Well, because we have 1, 2, and 3, so 3 areas where we're charged up. We have 2 bonds because it's going to be the oxygen here and oxygen there. And then we have 1 lone pair from the nitrogen, which is in this case right there. And so in this case, it's called a bent structure. So a bent structure basically would be one where the actual electrons on the nitrogen are bending the entire structure. So because of that, what we're going to have is a 120 degree angle as well. So we're going to have an ideal bond angle of 120 with the lone pair pushing through the side. So very similar to the other situation where we had 3, but here what the lone pair does is that it pushes these 2 down, creating that bond angle. So the repulsion that you're actually getting from here, that bond angle is really created from that electron pair pushing on the electron clouds on this side. Now let's take a look at 4 charge clouds with CH4. This is a situation where we have 4 hydrogens around, and again we're going to count the lowest dot 2, 4, 6, 8, and hydrogen does not need 8 electrons, so it's a full octet already. It's one of the exceptions to the rule. So we have 2, and in this case we have 4 charge clouds. So again, we're defining a charge cloud as how much electrons does carbon have that's come in contact with. So it comes in contact with 1, 2, 3, 4. And what happens is we have 4 bonds, 1, 2, 3, 4, and then we have no lone pairs for the carbon, which we already know because carbon has a full octet. So because of that, it's considered to be a tetrahedral. Now the word tetra means 4, so hedral is obviously a tetrahedral shape. And then when you take a look at the bond angles for those are going to be straight up 109.5. So memorize the 109.5 bond angle, where we don't have any lone pairs in this case. So this is not a lone pair, and they want to be maximum away from each other at about 109.5 degrees. So 109 is going to be the tetrahedral shape. Now let's talk about the situation where we have a tetrahedral, but now we have 4 charge clouds. In this case, we have the electron pair here. We have 3 of the bonds. And then that example is going to be ammonia, which is NH3. And this one is going to have that lone pair, which you can kind of guess that it's going to start pushing this thing around compared to the other example, which is your methane, which is the CH4. So this lone pair is going to do a couple of weird things to the entire molecule and distort it. Now in this case, we have 4 charge clouds because we have 1 here from the electron, 1, 2, 3, and 4. And then we have 3 bonds, which is 1, 2, 3, and then 1 lone pair, which is coming out from the nitrogen. In this case, we have trigonal, pyramidal. Now notice the other one was trigonal, just, straight up planar. This is going to be pyramidal because what it does is that it forms an actual pyramid from the top here, and then the nitrogen's sitting on top, so it forms like this trigonal 3 atom, and it forms this pyramid that kind of sits on top. So if you visualize this by pulling this into a pyramid, you can kind of see that. So with that, the bond angle is going to be about 109.5. Okay, so again, very similar to the other example where we're looking at that 109.5 degree bond angle. So that's going to be the ideal, because what happens here in the trigonal pyramidal is that lone pair pushes these bonds aside and then creates that 109 area. Now, when we're talking about 4 charged clouds now, and we're talking about water, H2O, 1, 2, 3, 4, you actually have the effect of 2 lone pairs pushing on that atom. And what's happening there is they were kind of bending the entire molecule. And when you do that, what you're going to end up getting is a lot of bond angles. So oxygen bends through here, and so what you're getting is 4 charged clouds, because you get two of these lone pairs in here, 2 of these pairs, and then you have the hydrogen. So what that creates is a bent structure. Okay, so the bent structure creates it with 4, because what you're really doing is you're kind of bending it down this way. So, and that's going to be a 2-2 situation. And in this situation, because they're getting bent, the actual bond angles are going to be, again, 109.5, but the actual bond angle is 104. So it's technically going to be a lot tighter here, about 104.5 versus the 109.5 that you would see in the other angles. So again, 104.5, 109. So the way I like to think of this is that the more lone pairs you have, the smaller that angle is going to be. So we're looking at that 104.5 versus the 109 because of that extra lone pair there. Okay, now for the AP exam, you do not have to know anything past the 4th 4 attachment. So we're going to skip over to this. So if you see a sheet with 5 or 6, you just kind of have to look at it, but you're not going to be tested on them. Okay, so in this case, we're getting a situation where we have compounds with multiple central atoms. And so if I have more complicated structures where we throw in more than one, things get a little bit tricky, because now at that point, you're going to have to do 2 Lewis dot structures. So the first thing is you want to look at the central atom at its own, and everything around it's considered to be a terminal atom. So the first thing you're going to do is you're going to count how many clouds you have and how many bonds around it, and then you want to predict the shape around each of the terminal atoms. And then from there, figure out what the central atom is, and then just go ahead and repeat each step. So let's go ahead and give you an example for this, and once you go through this, you'll see the exact series of how you're going to be doing it. So again, we're looking at the central atoms and then finding out what's around them, and you're going to have these multiple shapes. So here's an example of a carbon. This is a very common type of molecule where you have carbon in the middle, and then you're attached by 2 other carbons. And so the question is, predict the shape around each of the carbon atoms in this compound. So in this case, we're going to look at the terminal. The central one is carbon here, but we also have CH2 and then a CH2 on the left and on the right side. So let's go ahead and discuss how we're going to go about doing that. So the first step we're going to do is we're going to isolate the terminal, and we're going to call this the trigonal planar. Why? Because we have 3 of them attached with no lone pairs. The carbon straight in the middle with 3 sections connected, which are these of your electron clouds, 3 bonds and a double bond. So we would call this a trigonal planar. We'll look at the second one is going to be linear because we have 3 C's across, and obviously we don't have any lone pairs, obviously. And then again, we're going to have another trigonal planar. So in this case, we have a pretty interesting molecule that has three VSEPR models, geometric models, I guess what you call it, where we have actually these conditions because we're looking at those terminal atoms. Now let's talk about hybrid orbitals real quick. And so hybrid orbitals, basically what they do is that around the central atom, you're going to get overlap of electron clouds. And so, as I was mentioning before, electrons exist in these kind of clouds. You put them all together, and what happens there is that they begin to actually hybridize.